Okay, so today we're going to talk about graphic displays for numeric and also categorical data. So we'll start off for numeric data and then later in categorical data. Oh, I forgot. This is the classroom with the terrible projector. So hang on. Where did it go? Okay. Larger pen. All right. So all right. Graphic displays for data, and we'll have numeric and categorical. Okay, so we're going to start off just rehashing what we discussed about numeric data. So as far as, or just in data in general, as far as data goes, the number of observations that we have in a sample is what letter? What letter do we use for the number of observations in a sample? N. Okay, so the number of observations in a sample is N. And so you could imagine, you know, here we have some data set, okay, and we've got many rows. Or here, maybe we just have a small data set, and we're going to just look at one column, okay? So, you know, there's other columns here and other columns, but we're just going to look at the column for age. And so let's say we have 4 values. One display is called the dot plot. Alright, and so we're going to just start off here, and I'll say 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, and then I'm going to draw a dot at 10, a dot at 12, a dot at 15, and a dot at 18. Okay, and this is a dot plot. You get one dot for each observation. Okay, and you can it works just fine even for larger data sets. We'll just have more dots. So, you know, you might get something that looks like okay, and this would be a dot plot. And again, across the bottom, you have basically just a number line indicating the value that appears. Okay, so this is just a number line. Number line across the bottom. Okay, and so this gives us an idea of the kind of how what values appear in our data set. Okay, so you know, if we were to put numeric values on our number line, okay, so we have 10, 11, and 12, etc., 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 we can see that the values 11 and 12 are much more common than these values over here, and these values over here are also quite common and things like that. So we can get an idea of the frequency of the values in our data set. Okay. So we have dot plots. We can also create histograms. Okay, and so a histogram, let me just start off with this. So if this is our dot plot where we've drawn a dot for each one, we can encapsulate these things into little columns. Okay, and then, so if instead, and then, so just imagine that the dots don't appear here. So this would now be a histogram, okay? Basically bars instead of dots. Bars instead of stacks of dots. Okay. But the advantage with a histogram is that, you know, if you have a large data set, you know, where you've got thousands of rows, you would need to have thousands of dots in your dot plot, okay? So for very large data sets, and I just want to make sure that my printing is legible for everybody still. Okay, those of you in the back, I got head nods, so we're good. Okay, so very large data sets, you know, a dot plot is less desirable. Okay, just because you're going to have thousands of dots. Okay, and instead, we can create histograms with bins. Okay, and so with a bin, basically, it's like a frequency table, and we're going to take the values and we are going to group them together. So for age, we could do like 10 through 19, 20 through 29, 30 through 39, et cetera, et cetera, et cetera, 40 through 49. Okay, and let's say we have 7 here. Okay. So this means that in our data set, there were 7 people with numeric values between 10 and 19. Okay, so, you know, perhaps I don't know, 11, 12, 15, you know, whatever, 17, 18, and 19, or so, okay? I'm just making up numbers. So there were just 7, okay? And then, you know, we can just go through and say, you know, there were 10 and 12 and 4 or something. And so in this case, our histogram would look something like this. And we would have 10, 20, okay, so 7 and 10 and 12 something like that. Okay. All right, and so this is a histogram that represents the information inside our kind of our frequency table for these named numeric ranges. Okay, we good? Great. And all right, and so let me also talk about stem plots, okay? And as far as stem plots are concerned, I really only see these appear in statistics textbooks. I haven't really seen them show up too much in real life. I mean, they're useful, but, you know, I've yet to see a newspaper article that makes use of a stem plot, okay? So let's just say, you know, as far as ages go, let's say we've collected data and we looked at ages and we got, you know, 10, 12, 17, 20, 22, 22, 29, 30, and 35, okay? And so what we're going to have is we're going to represent each of these values with 1 on the tens side, and then what I'm going to have is I'm going to put the value 0 here to represent the number 10, okay? And then to represent the number 12, I'm going to just put a 2 in this same row. And to represent the 17, I'm going to put a 7 in that row. And then I move on to the 20s, okay? And then so I'm going to put in a 0 to represent this value of 20. I'm going to put in a 2 to represent this 22, and then put in another 2 to represent this 22, and then I'm going to put a 9 to represent 29. Okay, so what goes in my last row here? 0 and 0 and 5, exactly. Okay, so this is what we have for a stem plot. Okay, if you have lots of values, okay, so with many values, you can create, you know, 2 rows for each tens place. Okay, and then so you would have basically 1, 1, 2, 2, 3, 3. Okay, and then you would only put in values 0 through 4, and then this would be 5 through 9, 0 through 4, and 5 through 9, etc., etc. Okay, and so my 0 and the 2 would show up here, but the 7 would go down here, and then the 0, the 2, and the 2 would show up here, but then the 9 would come over here, and then the 0, and then the 5. Something like that. Okay, so both of these stem plots represent the same information. Okay, and if you think about it, a stem plot is just really, it's kind of like a histogram. Oops. Okay, so if I just rotate it and turn it on its side, and then I draw little boxes around it. Okay. Okay, so we have this, and there you go. And this is, like a histogram. Okay, but it shows you the individual values. Okay. So far, so good? All right, okay, so the reason why we want to display all of this data, okay, so we like to display our data because we can then describe the distribution okay, and what do we mean by distribution? The distribution can be something like, how the values in our sample are distributed, okay? Okay, and so perhaps we could look at the heights of U.S. males. Okay, and it looks something like this. I'm just making up stuff here. Okay, and so in the U.S. the average height of males is something around 5'10". So I'm going to just put like 70 inches, maybe a little bit shorter than that, maybe somewhere between 5'9" and 5'10". Okay, and then as we go higher and higher, this graph is not very accurate, but I'm just doing it as such. Okay. What we're saying is that heights in this range are most common. Okay. Okay, and they're most common because the bars are the tallest here, right? Okay, and then out here, the bars are shorter, indicating that these heights are less common. Okay, same thing down here. Okay, and so that's what our histogram represents, and this gives us an idea of, if someone were to ask, how are the heights? What's the distribution of heights here? We would say, oh, okay, well, these heights are quite common, these are less common, and so on and so forth. Okay, and so we can summarize this with just kind of this curve. And maybe that's. So we can create a curve that looks something like this. And this would be, so this is kind of just a summary curve of this thing. And we might say this is unimodal and symmetric. Okay, so as far as when we're talking about symmetric, I'll talk about this idea of what's symmetric versus not symmetric, and then we'll talk about unimodal versus other modal things. Okay. Can I flip to the next slide here? Okay, so if we have symmetric. So, this would be something that's unimodal and symmetric. Basically, we're going to say, something around here, this is the middle, the concept of middle. And then out here, this is, above the middle. And we have below the middle. Okay. And in this diagram, we have something that's symmetric and it's unimodal. So what this means is that values above the middle are less common, but also values below the middle are equally uncommon. Okay, so these have are about as equally common. Okay, so these values above the middle are slightly less common. These values below the middle, slightly less common. That's what we might say if it's symmetric. Okay. On the other hand, if I may flip to the next slide, we could have something that is skewed. Okay. So let's see. So I could have this. Okay, this would be what we could call right skewed. Actually, probably it looks better to go like that rather than. Okay, and so with right skewed, and if you need help remembering, just imagine stabbing something, okay, with this shape here. The side that you would use to do the skewering or the stabbing would be the right side, okay? So this is the right tail. The tail is over here. If you had to do any kind of skewering, you would use the right side, okay? And so if we think about, you know, kind of what's typical or what's the most common values, that would be something around here, okay? So this can be thought of as, quote unquote, the idea of the middle, or this would be, you know, kind of our typical values. Typical values here, these are the ones that are most common. And what we have is we have some values that are far above the middle, okay? So this is, you know, values far above, okay, are less common, but they do exist, okay? Okay. On the other hand, if we try to go, if we look at how far this is above the middle, if we try to go that direction below, there's nothing out here, okay? So there's nothing that far below the middle. All right, and so we can think of you know, an example that is right skewed is income. Income, you can think of, you know, what's the typical annual income of someone is probably something around $50,000 to $60,000 a year, something around there, typical. So maybe average can be, you know, I don't know, 55,000. All right. Are there people who make $1 million a year or more than $1 million a year? Yes. Okay. So, you know, you could have someone out here who's like making $1 million a year. Some people, not many, but some people make, you know, $1 million per year. Okay, so $1 million would be, you know, 945,000 above average. Okay, this would be, you know, this is 945,000 above average. Okay, so if you think of what's 945,000 less than average, that's something like negative $890,000. Okay, so can anyone make negative $890,000 in their for their annual wage? No, it's not legal to make someone go in debt for working. Okay, I mean, that's that. Okay, so I'll write no one makes negative, you know, 890,000 per year per year. Okay. Yeah, you might have people in debt, but they are not getting paid debt, okay? So that's what we have there. Okay. So this would be right skewed, all right? So if that's right skewed, then this would be what? Left skewed. All right, great. Okay, and left skewed, this could be something like maybe scores on an easy test. So if it's an easy test, probably most students are going to score like 90% or something, okay? But you can't get higher than a perfect score, okay? So it's not possible to get higher than a perfect score, but you've got a lot of people getting high scores. So the bulk is up on the high end. But even if it's an easy test, there's inevitably some students who do poorly, that, you know, maybe 30%, 25%. So they are far below the average, okay? So if someone gets 20% and the average is 90, that person is 70 points below average. 70 points above average would be 160%, which is not going to make an appearance on our graph. Okay, so that's what we have there. That's left skewed. Okay, all of these have been unimodal. Unimodal, or this idea of modality, talks about, you know, the number of peaks. So here we have one peak in our numeric distribution, or our numeric data. So so that means, you know, one value is most common. One value, or, you know, one range of values. Okay, and then all other ranges are less common. So everything that has just one peak, so basically like one hill, these are this is unimodal symmetric. This is unimodal right skew. Okay. And we have things that are uniformly distributed. Okay, so this would be uniform distribution. Okay, so this, you know, the height is the same across the board. This means all values show up with equal frequency. So perhaps something like last digit of your phone number. Okay, so we would expect approximately the same number. The number of people whose last digit is 1 is going to be about the same number of people whose last digit is 9. Okay, that's what we're anticipating for something like that. So that'd be a uniform distribution. Or, you know, if, how long, you know, if you, yeah, if you go to, stand in line at a, I don't know, fast food place, the question would be, how many people are in line ahead of you, okay? Well, actually, that's not going to be uniform. Certain values are going to be more common than others, so never mind. Take that back. Last digit of your phone number, that one works for uniform distribution. Okay. All right, and so this is we have a bimodal distribution. Okay. So this one means 2 peaks. 2 peaks here. Okay. And so for bimodal data, we have, so keep in mind, so what this means is you've got 2 peaks showing up in your numeric data. Okay, so we are still just looking at one numeric variable, but within that numeric variable, there are 2 values that are both quite common. Okay, one numeric variable, okay, but within the numeric variable, there are 2 values, or ranges, that are quite common compared to others. Okay, and so this is my example that I used last class that may have been insensitive, but just from a medical standpoint, this is a observed phenomenon, and I don't know exact values, but we could look at testosterone levels in people. Okay, and so everyone should produce testosterone in their body. Okay, and in general, men or people who identify as men will produce more testosterone in general, and women generally produce less testosterone. Okay, and so I'm just making up numbers here, but we could look at just one numeric column here for a testosterone level. And I'm making, I don't know exactly how this is measured, but it's probably concentrated as like deciliters per gram or something. And so maybe the levels are something like 12, 15, 10, and then maybe we have 65, 68, 70, and then 13, 14, and 77 or something like that. Okay, so if we assume a gender binary system here, we can just by looking at these numbers, we can kind of take a guess and guess who might be female and who might be male, just from looking at these values, even though we haven't asked the actual question of are you male or female. Okay, just from looking at testosterone levels, we might be able to guess. Okay, and it's probably not it's not going to be the full proof. It's not going to be 100% accurate or anything like that. But if we were to graph this, okay, we would see something that appears like this. Okay, and so values around here, I don't know, 65 or whatever, I'm just making up a number. This can be thought of as the quote-unquote average or typical level of testosterone in a male. Okay, and then values over here, so let's say 12. Okay, this can be thought of as the typical average or typical level of testosterone in a female. Okay, but of course there's variation all across the board. Okay, you can have someone out here, probably a male with relatively high testosterone compared to other males. Okay, someone down here, probably female with relatively low testosterone. Okay, and then someone, you know, out here could be a female with relatively high testosterone compared to other women, or it could be a male with relatively low testosterone compared to other men. Who knows, okay? So this it could be, you know, male with relatively low testosterone or female with relatively high testosterone. Okay, and so this is just, you know, this is just an example in terms of a numeric variable that is bimodal. Okay, and so, you know, I know this is kind of, life is more complicated than just a simple binary yes or no, or one category or the other. But you know, if you look at if we were to look at the distribution of testosterone levels in the medical research and things like that, we would see something like this, okay? And so this would be a bimodal distribution. Is that okay? Are there any questions? I don't know when that door opened there. Okay. All right. So then, okay. So then now I'm going to talk about categorical variables and displaying categorical data. All right. So as far as categorical data goes, we have, you know, to summarize our categorical data, what can we make? To summarize, as far as tables go, we can create I'll tell you, all right, a frequency table for categorical data, okay? And so let's say, you know, let's say we're talking about some flower, okay? So we got flower type 1, flower 1, and let's say we're looking at the color of the flower, and we've got red flowers, pink flowers, and white flowers, okay? And we'll look at the frequency of flower 1, and let's say there's 10, 70, and 10, or maybe we'll say 10, 70, and 20, okay? And then so to display this, we can create a bar chart. So 70, you know, 10, 30. All right, and then so I've got red, pink, and white. 10 red, 70 pink, 20 white, okay? And then over here, maybe we have flower 2, and we look at the colors of the flowers. We got red, pink, and white flowers over here also. And the frequency will be 30, 30, and 30. Okay, and so all of these, oops. Okay, so we got, so we have this. All right, and so the question I pose to you guys is, which flower has more variation in color? Flower 1 or flower 2? Which one has more variation in color? 1, 2, okay. And, all right, and so the answer is flower 2 has more variation in color. Now, why is that? So you might look at flower 2 and you'd say, well, I got 30, you know, all the numbers are 30. Okay, how's that more variation? Okay, well, that's actually, when it comes to categorical variables, to have your different categories equally represented is kind of the situation with the most variation, or the quote most diversity in the categories. Okay, so over here, if you were looking at flower 1, you know, your really only options are pink flowers. Okay, yeah, there are red flowers and white flowers, but they're hard to come by. Okay, and so if you wanted to shop for flower 1, you're most likely going to get a pink flower. Okay, if you're shopping for flower 2, your options are red, pink, and white, and they're all equally available. And so if you wanted to create an arrangement of red, pink, and white flowers of flower 2, that's a lot easier to do so. Okay, whereas with flower 1, you're really limited in your options there. Okay, so we would say flower 2, in a situation for categorical variables, flower 2 has more variation in the color. Okay, and this can be generalized to any set of categorical data. Okay, if you've got you know, just one category kind of being dominant, then you're going to have less variation, and if you've got all the different ones showing up equally, then you got more variation there. Okay, that's it. We'll see you guys on Monday. Have a good weekend.